In 1896, an American economist wrote down an equation with 4 letters in it. MV equals PT. It looks almost embarrassingly simple. The kind of thing you'd expect on the first page of an introductory textbook, not the kind of thing that could quietly explain everything we've talked about on this channel so far. But here's what almost nobody tells you about this equation. It isn't really an economic theory. It's a conservation law. The same kind of law that governs energy in physics. The idea that energy can't be created or destroyed, only transformed from one form into another. Money, it turns out, may obey the exact same structural logic. And for over a century, this connection has been sitting in plain sight, occasionally rediscovered by a physiologist here, a Nobel laureate there, and then quietly forgotten again by mainstream economics. If you've watched our last few videos, the physicists on Wall Street, the formula that broke the market, the sample explaining every crash, the thermodynamics hiding inside Bitcoin, this is the video where all of those threads finally tie together. Because underneath every one of them is the same idea, showing up again and again in a different costume. Let's finally look directly at it. The equation is called the equation of exchange, and it was formalized by economist Irving between 1896 and 1911. In its simplest form, it reads, M times V equals P times T. Money supply multiplied by velocity, how fast money changes hands, equals the price level, multiplied by the total volume of transactions in an economy. Here's the detail that changes everything about how you should think about this equation, and it's the very first fact worth knowing. Fisher never originally framed this as a predictive law. He framed it as an accounting identity. That distinction matters enormously. A predictive law tells you what will happen next. An accounting identity simply guarantees that both sides of the equation must balance always, by definition. The same way the first law of thermodynamics guarantees that energy entering a system must equal energy leaving it, plus whatever gets stored inside. It doesn't tell you why the energy moved. It just guarantees the book's balance. Fisher's equation works the same way. It doesn't tell you why money moved. It just guarantees that however money moved through the economy, the two sides of that equation must match. That's not a small technicality. That's the whole reason this equation might be far more fundamental and far more physics-flavored than most economists ever gave it credit for. Let's make that connection explicit, because it's not a loose metaphor invented for this script. It's an argument that's actually been published in serious academic work. In a 2021 review, physiologist David C. Dawson explicitly argued that Fisher's equation of exchange is structurally analogous to the first law of thermodynamics. Both are conservation-style identities. Both balance a flow rather than explaining its cause. Both simply insist that whatever goes in and out of a system must add up. This is a genuinely deep structural parallel, and here's the part that should bother you a little, the way it bothered us. It is almost never taught in economics curricula, not as a footnote, not as an aside, essentially absent. Generations of economics students have learned Fisher's equation as a dry, standalone formula for inflation, without ever being told it belongs to the same mathematical family as one of the most fundamental laws in all of physics. Here's where the story gets even stranger, because this insight wasn't just made once and ignored. It was independently rediscovered, and then ignored again. Thomas Schelling, a Nobel Prize-winning economist best known for his work on game theory and conflict strategy, independently suggested in the early 2000s that Fisher's equation mirrors thermodynamic conservation laws. Schelling wasn't citing Fisher's original intuition. He arrived at essentially the same structural insight on his own, roughly a century after Fisher's original formulation. Think about what that actually means. Two brilliant economists, working almost 100 years apart, independently noticed the exact same thing: that money, structurally, behaves like a conserved quantity. And both times, the insight failed to reshape how the field actually teaches or applies the equation. That's not a coincidence you'd expect from a trivial observation. That's the signature of something genuinely important that keeps slipping through the cracks of how economics organizes its own knowledge. Now here's a timeline detail that deserves to stop you in your tracks. Fisher's monetary equation was formulated between 1896 and 1911. Einstein's mass-energy equivalence, the famous E equals mc squared, arrived in 1905, sitting right in the middle of that same window. Two of the most consequential conservation-flavored equations of the early 20th century, developed almost simultaneously in completely separate fields, with essentially zero cross-pollination between them. For over 100 years, these two equations sat in isolation from each other, one governing energy and mass, the other governing money and transactions, never formally unified. Then, in 2023, researchers finally proposed a direct bridge, a money-energy model, applying the mathematical framework of special relativity directly to monetary policy, using variables explicitly modeled on relativistic mass and velocity, but applied to inflation and the speed of money instead. We'll get into exactly what that formula looks like a little later in this video, because it's genuinely one of the strangest, freshest ideas in this entire body of research. If this equation is this elegant, this deeply connected to physics, why isn't it the centerpiece of every economics course on the planet? Here's where the story takes a very human turn. Despite its structural elegance, Fisher's equation was largely overshadowed in the mid-20th century by Keynesian macroeconomics, a school of thought that shifted focus toward aggregate demand and employment, rather than monetary conservation identities. Keynes's ideas dominated the conversation for decades, and Fisher's more physics-flavored framework quietly receded into the background. This is worth sitting with for a moment, because it's a pattern you've probably noticed on this channel before. Powerful, elegant frameworks don't always survive because they're correct. Sometimes they survive or fade, based on which intellectual movement happens to capture the field's attention at the right historical moment. Fisher's equation didn't get disproven. It got outcompeted for mindshare. Here's a flaw hiding inside how this equation gets used today, and if you've watched our Black-Scholes video, this pattern should feel uncomfortably familiar. A core assumption baked into early quantity theory is that velocity, how fast money changes hands, is stable, constant, predictable enough to treat as a fixed number in your calculations. In reality, velocity fluctuates wildly. It shifts with financial innovation, with crises, with the sudden rise of digital payments changing how quickly money moves through an economy. And yet, many textbooks still quietly treat velocity as fixed, purely for the sake of mathematical simplicity. This should sound exactly like the story we told about Black-Scholes, an elegant model built on a simplifying assumption that's usually close enough to true, until precisely the moments when it matters most, when velocity swings wildly and the entire equation's practical usefulness quietly breaks down. Most popular explanations of Fisher's equation quietly simplify it down to 4 letters. mv equals pt, but the full version Fisher actually proposed is richer, and almost nobody outside specialist circles ever sees it. The complete equation reads, mv plus m prime v prime equals pt. That second term, m prime, v prime, accounts for bank deposits and their own separate velocity, distinct from physical cash and its velocity. This dual-layer structure, physical currency moving at one speed, bank deposits moving at another, both feeding into the same overall balance, is almost never highlighted in popular discussions of this equation. It's a small detail with a big implication. Fisher wasn't just describing physical cash in your pocket. He was describing an entire layered monetary system, decades before most of that system's modern plumbing even existed. Here's a piece of history that connects this equation directly to real, consequential policy decisions. Fisher himself used this equation to argue for monetary stability under the gold standard, using the conservation-style logic of his own formula to make the case for tying currency directly to a physical, tangible anchor. But after fiat currencies became dominant following 1971, when the last formal ties between the US dollar and gold were severed, the equation's policy relevance faded from mainstream discourse. It didn't disappear from economics entirely, but it stopped being the center of the conversation it once was, precisely as the monetary system it was originally built to describe started operating on fundamentally different terms. Here's a genuinely uncomfortable admission buried in the modern academic literature, the kind of thing that should make you raise an eyebrow. Dawson's 2021 paper explicitly notes that, like thermodynamics' energy conservation law, Fisher's equation does not specify causality. It doesn't tell you what caused a change in prices or what caused a change in output. It only guarantees that the two sides of the equation balance. And yet, policymakers continue to use it for inflation targeting, as though it were a causal, predictive tool, rather than the accounting identity it actually is. This is precisely the same trap we explored in our Black-Scholes video, a genuinely powerful, mathematically sound tool, being used slightly beyond what it was actually designed to promise. The equation isn't wrong. The confidence people place in what it can tell you sometimes outruns what it was ever built to deliver. Here's where the physics parallel gets genuinely precise, not just poetic. In Econophysics, the structure of mv equals pt is mathematically identical to the continuity equation used in fluid dynamics, the equation stating that mass flow rate equals density, multiplied by velocity, multiplied by cross-sectional area. That's not a loose comparison. It's the same mathematical shape, describing two completely different physical systems, fluid moving through a pipe and money moving through an economy. This is precisely the kind of universality we explored in our video on market crashes, different systems, wearing completely different costumes, obeying the exact same underlying mathematical structure. Money, according to this framing, behaves like a conserved fluid, flowing through the pipes of an economic system. Let's come back to that 2023 breakthrough we teased earlier, because this is genuinely some of the strangest, freshest territory in this entire video. A 2023 paper introduced a formula for what its authors call money energy, written as E sub m equals a function of m sub I and c sub m in plain language. Money energy depends on something the authors call the mass of inflation, and something they call money speed, variables deliberately modeled on Einstein's relativistic framework of mass and the speed of light, but reapplied to monetary policy instead. This is virtually unknown outside niche econophysics circles. It's speculative, genuinely new research territory, not an established, widely tested framework the way Fisher's original equation is. But it represents something worth appreciating regardless of whether it eventually holds up under further scrutiny. A serious, ongoing attempt to finally unify two equations that predate each other's field, sat isolated from one another for over a century, and might be describing the exact same underlying structural logic all along. Here's a detail that reframes how impressively early this equation actually was. Fisher derived his equation decades before modern national accounts, GDP as we understand it today, were formally defined, which didn't happen until the 1930s and 40s. In his original formulation, Fisher used T for total transactions rather than Y for output, as later monetarist reformulations would use. That distinction matters more than it looks like on the surface. Total transactions is a broader, more encompassing measure than output alone. It captures every exchange happening in an economy, not just the final production of goods and services. Fisher's original framework was, in a real sense, more comprehensive than the narrower reinterpretations that came after it. Speaking of narrower reinterpretations, let's talk about the most famous one. Milton Friedman revived Fisher's equation in the 1960s through the 1980s under the banner of monetarism, reducing Fisher's richer identity down to m times v equals p times y, with y representing real output. Friedman assumed stable velocity, using this simplified version to argue that inflation is, in his famous phrase, always and everywhere a monetary phenomenon. This oversimplification helped make the equation more usable for policy, a genuinely important contribution. But it also obscured the equation's deeper structure. The dual-layer M'-V' term describing bank deposits quietly dropped. The broader T term, replaced with the narrower Y, a rich, physics-flavored conservation identity, compressed down into a more digestible but noticeably thinner policy tool. Here's maybe the single strangest fact in this entire list, and it says something quietly damning about how modern academia organizes knowledge. The most detailed modern analysis treating Fisher's equation as a genuine thermodynamic analog didn't appear in an economics journal at all. It appeared in the American Journal of Physiology, Cell Physiology, in 2021, written from the perspective of someone studying biological systems, not monetary policy. Think about what that means. The most rigorous treatment of one of economics' foundational equations, reframed correctly as a conservation law, came from outside economics entirely. That's not a minor curiosity. That's a genuine institutional blind spot, a 100-year-old insight, sitting closer to a biology journal's shelf than an economics department's core curriculum. And here's the sentence that ties this entire pattern together in one blunt observation. Despite the thermodynamic analogy being explicit in scholarly work, introductory and even advanced economics textbooks still do not present Fisher's equation as a conservation law, not as a footnote, not as an aside. It's simply absent, a missed opportunity to teach economics as a genuine system of flows and balances, the same way physics teaches energy. Two quick, genuinely fascinating footnotes before we bring this all together. First, cryptocurrency white papers frequently use MV equals PT, or close variants of it, to model token velocity, supply, and price stability. If you watched our Bitcoin video, you already know this territory well, and yet these white papers almost never credit Fisher, or acknowledge that they're leaning on a 100-year-old piece of physics-flavored economic theory. Second, early 20th century economists actually debated naming this the monetary conservation law outright. They ultimately settled on the far more modest, more cautious equation of exchange, specifically to avoid implying causality it couldn't actually deliver. That single naming decision, choosing caution over a bolder, more physics-forward label, may have quietly shaped how seriously this equation's deeper structure got taken for the next 100 years. Now let's do something we haven't done yet on this channel: connect every thread. In our very first video, we showed you that Wall Street increasingly hires physicists because trading has quietly become an engineering problem wearing a finance costume. In our Black-Scholes video, we showed you an elegant model whose assumptions, treated as permanent truths instead of simplifications, helped nearly break the entire financial system. In our crash video, we showed you that market collapses may belong to the same universal family of equations as avalanches and earthquakes, different systems, same underlying mathematics. In our Bitcoin video, we showed you that a monetary system's security can be a direct, literal application of the second law of thermodynamics. And now, sitting underneath all of it, is Fisher's equation, a conservation law for money itself, structurally identical to the first law of thermodynamics, mathematically identical to fluid dynamics, independently rediscovered a century apart, and still, somehow, absent from the textbooks that should be teaching it as exactly what it is. The pattern isn't a coincidence anymore. Physics and finance aren't distant cousins occasionally borrowing metaphors from each other. They may be describing the same underlying reality in different vocabularies, to different audiences, for entirely historical and institutional reasons that have nothing to do with which framework is actually more true. So here's what I want you to walk away with today, and it's bigger than any single fact in this video. Money isn't just a social convention, or a government decree, or a speculative game. At a structural level, it may behave like a conserved quantity, flowing, transforming, balancing the same way energy does, the same way mass does, the same way fluid does through a pipe. That's not poetry. That's a century-old equation, independently rediscovered by a Nobel laureate, formally analyzed by a physiologist, and still missing from the textbooks that should have been teaching it as physics all along. The next time someone tells you economics and physics are separate disciplines, remember, the equation was there in 1896. Einstein's equation arrived almost simultaneously. Nobody connected them for over 100 years, not because the connection wasn't real, but because nobody was looking in both directions at once. We started this series asking why Wall Street hires physicists instead of MBAs. It turns out the answer was always bigger than hiring practices. Money, markets, and energy may be speaking the exact same underlying language. We've just been too specialized for too long to notice. If this kind of thinking, where physics quietly explains the parts of finance nobody else is willing to explain, is why you're here, subscribe. New videos every week, breaking down the hidden math behind money. See you in the next one.